Hello and welcome. Today we are talking about uh, hexagons, or more precisely, how to draw perfect hexagons using my hexagon calculator and explaining how my hexagon calculator works, and we can get into the mathematics behind it. First off, I'm showing off what I have made. I'm calling this one the vertical hex sheet. This is going to be a printout that will be available. It is designed specifically for 8.5 by 11 inch printer paper, standard printer paper. I'm calling this one vertical because if you really look at the lines are going downwards. If you understand what I mean, understand what I'm saying, the hexagons are in line going down. And I'm calling this other one here horizontal because the hexagons are in line going left to right. So today, I'm also calling this I'm also going to call this these half-inch hexagons. I'm calling these half-inch hexagons because from here to here is a 1/4 inch, so from here to here is half an inch. This is half an inch. From there to there, to there to there, and there to there. So I'm calling these half-inch hexagons. Today you'll be able to watch me make a grid of hexagons in Krita using my calculator for 1-inch hexagons, roughly the same thing as this. So without further ado, let me show you my hexagon calculator. Hopefully we can get through this in one take. Here's the calculator. It looks funny, I'm sure. And why don't we try to increase the size of it? This is just what it looks like on my screen. I can do this. We'll make it a little bigger so we can walk with it, so you can see what I'm doing. So we are wanting to make 1 inch at my printer is 300 dpi. That's pixel density. So 1 inch at 300 pixels per inch density. Calculate. And what that did was it ran a whole set of calculations in the background, which we will review in just a moment. But what we got out was, if we put in 1, that is C, this is C, 1 is this side, or half of this, or half of this, it's this side. A hexagon, a hexagon is, I'm not sure you can see where my mouse is. Yeah, you can't see where my mouse is, I'm sorry. To be more precise, the C is equal to every side of every equilateral triangle that I use to make a perfect hexagon. So to get into the mathematics, and understand the math, a hexagon can be created out of 6 equilateral triangles. And equilateral triangles are called that because all sides are the same size. With that being said, C is equal to twice what A is on this sheet. So, and then if we expand A all the way across, that would be twice the size of C. But what we need for the perfect grid is the B. Now, to get b, I apply Pythagorean theorem in reverse, which due to running it in reverse to get the correct answer, we will end up having to multiply the Pythagorean theorem answer for b by a multiplier of 10. I'll explain shortly. But if we look, 1 inch at 300 pixels per inch at C, we got, if we look at this, we got inches, and then do it like this. If we look, we got inches, then we have A, B, C, then we got pixels, A, B, C, and then the DPI is set at 300. So at 1 inch input at 3 DPI, that is for C. It is 1 inch C, half inch A, because A is half of C, because we cut the equilateral triangle in half into a right angle triangle. Now, that's how we can apply the Pythagorean theorem. Good old Pythagoras, I like him. He believes all of nature, all of reality can be explained with numbers. It's all numbers, he believes. Anyway, so then by doing the Pythagorean theorem backwards, instead of doing a squared plus b squared equals c squared, I took the square root of c and minus the square root of a to get the square root of b. Now, because I did it in reverse, for some reason it always comes out as 1/10 of what it needs to be. So I have to multiply it by 10 to get the decimal in the correct place. Because, like I said, I'm doing the Pythagorean theorem backwards. I don't know why I have to add a multiplier of 10. I'm sure there's a reason. Anyway. Now, all these numbers I just calculated are not in the inch category. I calculated the pixels. I took 1 inch, I multiplied it by 300 dpi, and that's why the C in the pixel section is 300, and that's why half of that in A would be 150 instead of 0.5. And then I guess a multiplier of 3 on the 300 of whatever is of B is 257. Anyway, we'll get into the code really quick, and then we're going to start drawing. So we'll just quickly check the code in the code editor. We can hide the calculator for now. Now, in the code editor, if we look here, it's Python. We import OS, we import system, we import my custom package, which we will get into shortly. It's right here. But my custom package, and inside the custom package we have, hold on, I need to get in here. Inside this custom package we have the int, which is important. It does any. It's actually blank inside. But that is important because it allows the package to be recognized by the code. But inside we have the window creation, the GUI setup, and of course the function, which is where we're going to do the mathematics. So inside Hexagon Calculator.py, we have this all set up. We import PyQt5. This is running on Python 3 and PyQt5. PyQt5 handles the windows, buttons, labels, images. It handles all the UI components. It's standard. I prefer PyQt5. Some people's moved over to a new type of Py. But anyway, we set up the application here with Q application, which is through Py or PyQt. Then the window is created through PyQt, sort of, but we go over to the window in the package system. And what we do here is we have the window variables of the window name of the Hexagon Calculator, the positions. I kind of like it in the middle of my screen at the top. And then, the size, it's, width of 384, height of 256. It's kind of small on bigger desktops. But anyway, we import the app in here, and we get create the window, set the window title name, then we set the geometry based on pose X and Y, and then size Y, width and height. Set window icon to Q icon, that's through the PyQt, and then we tell it to show on the screen, and it returns back to this code. So now the main code has the window created, and it has the application and window created. It sends it to the GUI builder, and that's just a done icon when it's completely finished, and this is closes app when all said and done. But anyway, now we're heading to the GUI, and inside the GUI we have some basic PyQt stuff. We have a package reference to functions, which is where I built the math and everything for the Pythagorean theorem and all that. But anyway, a lot of PyQt stuff, integers, double validation for floats for the decimal point values, labels, widgets, icons, fonts, push buttons for the button. Anyway, we got the background color black, label color, whatever, label, font and size. Then we got button style, color, background, font and size, and a pixel. I forget what a pixel is. That may be an unused variable, but I'm afraid to delete it on stream. We're going to go past that. I'm going to double check that later. That might be for something that I can't think of right now. Anyway, then we got the background image of the hexagon, just to show what's happening, and give a visual clarification of A, B, and C. And then here's like the labels. The labels for inch and of different sizes and length and DPI. Anyway, when we get in here, goes to the build GUI, which brings in app and window, and then it makes those global variables so it can be accessed through here. Then it does the create GUI component, then it creates the box for the DPI, and then it creates box for scale. But anyway, create GUI components, we got, what is this? Pixel GL. I don't know what this is. Pixel GL. Oh, label Pixel GL. I'm still not sure what this is at the moment. Anyway, we got the image for the hexagon. We got the global box. This sets up the text box for putting in variable. This is a calculation button. This is all the inch information. Inch, A variable, B variable, C variable. They get toned into strings so they can be read. Same thing for label. All that happens down here. Style, font size. Qt core align left, puts it kind of all aligned on one side. DPI, all that's the same. And then it creates the... Okay, here we go. Creates these boxes, Q box, Q combo box. The combo boxes are the things that you click on and then they drop down, where you saw where I could change the DPI and change the inch to pixel. That's just for inputs. And here's kind of how it configures it. 0 for the menu item, and 1 is 150, 2 is 300, 3 is 600, and 4 is 1200. And it goes through this and it sets those. Same thing happens for scale, inch and pixel, it gets set. Then we run the function when the calculate button, where is it? Calculate button, when it gets clicked, connect, run function. That runs this function up here, which does a global on length, and it holds length as a data or as a variable for the text box for length.text, and then it runs function. It goes functions, which we're going to go into next in just a second. Functions run, and then it inserts the length, the preset scale, and the preset DPI based on the combo boxes. So then we go in here, and it's run, pulls in length, preset scale, preset DPI, and it checks the preset DPI, and based on the preset DPI, it will set the DPI as which is going to be a multiplier, which we'll see later. That's important. The DPI is the multiplier for the amount of pixels per inch. Pixel density per inch is how I see DPI. It really means something else, but that's what I call it. It's a 300 by 300 pixels per square inch is how I see it. Anyway, then it does, checks some things. Then it does a preset for scale. Are we doing the inch calculation or the pixel input calculation? Because that changes it a little. Changes our order of operations slightly. But anyway, we'll either go into inch or we will go into pixel with the length and the DPI. And then we'll drop down to the bottom here. And this is where the mathematics gets very interesting. So if we did inch, which we did this time, pixel will just do it kind of different and switch the pixels over to inches. Or it won't switch the pixels over exactly, but anyway, I'll explain that in a minute. Inch calculation, it takes the input, it takes the input in the DPI. It holds on to the DPI until we start pushing for, until we start calculating inches. Because we're in inches. What we do is, we're in inches, C inch is equal to the number that just got put in. And we're going to round that number to the second decimal. And then we're going to calculate the pixels, which will be rounded to 0 because they are pixels. You can't cut a pixel in half. We round those to 0. And they're already going to be multiplied by the DPI, which is 300. So, if we put in 1 inch, that gets multiplied by the DPI of 300. 1 inch is 300. Okay, so if it turned out that 1 inch equaled 301, or 300.5, it's like we don't need it telling us it's 300.5 or something stupid. We'll just say it's 300 whatever. It's fine. It's fine. We don't need to complicate calculations. We're not physicists. Then we calculate using the C pixel. We go and calculate the A pixel, which we know is half. If we pull up the hex calculator again, we can see the with the hex calculator we can see that the A is equal to, we see A is half of C. That's very basic, so we have it. And where are we? There we go. I got like 7 different windows open, and I have to keep switching between them to make sure I'm doing what you can see that I'm doing. So anyway, uh, that's half. So that'll cut the 300 of CPX to 1.5 APX, which is A pixels. And then that we will then divide by the DPI. So 150 pixels divided by 300 DPI, that is 0.5 inches. So it'll be 0.5, and that's why we have let it round to 2. We could let it round to 3 if we wanted. But really, we're going to be doing the mathematics in pixels because the pixels are the larger number. If we use pixels, which are the larger number, for the mathematics of square roots, we will get more accurate. But it doesn't have to be so accurate that we have to, can't round it to, pixels down, because we're already using a multiplier of 300%, or 300 times the initial thing. That would actually be 30,000%. So we're not concerned with that. So then we go and we're going to apply the Pythagorean theorem in reverse. We're going to do this in reverse because we're going to do c squared times, or c squared minus a squared, which is half, and then come up with b squared, which you're not supposed to do it that way, but I have found you can get a fairly accurate result by then multiplying by 10. Because for some reason, because you're doing it backwards, it pumps out, it's always down by 1 decimal. The answer is always down by 1 decimal. I've never figured that out. I'm sure there's a reason for it. I'm sure I could look up why. But it's usually accurate enough for my purposes. I'm sure a mathematician is probably freaking out right now if they watch this. Anyway, then we can take, by doing the Pythagorean theorem backwards, which we'll look at, we will get the b in pixels, bpx. And then we take bpx and we times bpx by, or we divide bpx by the dpi, which will then, reduce it by, divide it by 300. That gives us inches, and then we can push the data. The data gets pushed back into push data, which up here it'll say push data, and then it'll present the data in the terminal. This was how I was debugging and running numbers, simple numbers, and running calculations side by side on paper to double check that these numbers were correct. So yes, I know this works because I've ran 3 sets of numbers through this. I understand what's going on. It's all giving me the correct feedback, same ratios, everything's good. That data pack, that's all pushed into a data pack of the inches and the pixels for A, B, and C, as well as the DPI. The DPI is, presented down here at the bottom. I think I'm showing, underlining it, sort of. I can't actually see it on my screen. Anyway, that's all packaged into a tuple, which is then sent back to update the GUI. The GUI, hold on. I'm using a graphics pin. Give me a second. Yeah, update GPU. I don't know if you can see all this. It's the same stuff. It's just, this equals this, that equals that. Same thing as when we set up the initial, except it's pumping the values in and reconfiguring it so you can see it in the user interface. Hold on. I opened up a bunch of windows I wasn't supposed to. Oh, way to go. There we are. So yeah, I can, we did 1 inch. Let's type 2 inches at 300. There it is. Watch this. Let's do 1 inch. Let's do 1 inch at 300. Okay. Now, if we do 2 inches at 600 dpi, we'll get roughly the same numbers. I think this one might be a little different right there, and that one might be a little different right there. Let's see. Ooh, that's a little different. Okay. 2 at 600 dpi. Oh, okay, I see. Okay, that's interesting. See, I can't quite. Ooh. Hold on, let's run it at 1. See, the inches are the same. The inches will always be the same, or should always be the same. Inches will always be the same. So now if we do a 5 and run at 0, there we go. 5, half of 5 is 2.5. So therefore the b, it gets all square rooted and stuff. 4.29, sort of. It's almost the same as this, but not quite. It's the ratio of about a ninth or 9/10 or something, or 8.5/10. I can't tell. But yeah, the DPI will only affect the pixels simply because the pixels are what you're drawing in an image to get the sharpest image. From what I read, 1.5 DPI is for posters, 300 DPI is for standard documents, 600 DPI to 1200 DPI is high resolution, is photos and high resolution photos. So really you only need 300 DPI, and I actually have it set up where if you have it set to DPI, hold on, let me look. I actually have it set up where if you just leave it on DPI, it auto sets as 0. If it's set as 0 on the DPI index, which is labeled DPI, it will set it to 300 DPI by automatically. Same thing with A or inch. Same thing with inch. I basically got it set up where inches are basically the default. So, yeah. Where was I? Yeah, so we went through the basic system. I'm just going to show off the actual mathematical functions really quick, and then we'll get to drawing. I'm going to try and chapter this. I don't know how to make chapters, but I'll figure it out, so make it easier for you guys. So, anyway, we went through all the push. Now, if we look at this, we have several main components in the mathematics field. We have multiply by DPI, divide by DPI, halves, and somewhere here we have doubles. Somewhere here we have a double. Or maybe I got rid of the double because maybe the double's arbitrary at this point because I was using I was trying to apply a way to use A, and that was silly. Anyway, we get double for no reason, I think, which multiplies by 2. Input multiplied by 2 returns value. Half divide by 2 returns value. Multiply by DPI. That's the thing I was talking about earlier. Your input gets multiplied by the DPI, which is the pixel density. Therefore, the pixels are equal to inches. Whatever it tells you the pixels are equal to the inches it tells you it's set at, which helps with applying a grid, which we will show off in a moment. Anyway, same thing with divide. Input divided by DPI, return value. Square root, that was basic. That was a simple, we had to import math, I believe. Yeah, import math, We had to just import some basic math and do square root is, input to math dot square root input returns the value, which will be the square root, measured in pixels, which are the bigger number, to give us a more accurate output of an answer when we convert it back to. That will convert a more accurate number to inches than if we calculated in inches and then multiplied it by 300 or whatever. It'll give us more accurate because we are running a square root calculation here. We are figuring out the square root. We are also now the Pythagorean theorem in reverse. Like I said, we're doing input A and input C, and we are minusing one from the other. So here I had to apply some globals of root A, or A root, B root, and C root, which are the square roots of A, B, and C. That's just declaring variables. A is equal to square root of input A, which input A, according to down here, is the APX. Input C will be CPX. And so back up here, we run the variables of input A that will be into the square root, which will be rounded to a third. We're rounding it. We're not physicists. We don't need 27 times past the decimal. 3 is fine. I mean, we could do 5, but seriously, 3 is fine. So it pushes it out, and then this, we do the same thing for C. So then we got the square root of A and C. Then we take C, which is the larger number, and minus A, which is the smaller number, and then we round it again to the third. So we're going to maybe lose just a little bit of height in this calculation, but maybe only like a pixel or two. It really not that big of a deal. Unless you get like really super tiny, like you're trying to make 1/10 inch of a pixel thing or something. I don't know. But then we have to square it. I didn't want to do. I don't know how to apply an exponent, so I just multiplied it by itself. And then, like I said, for some strange reason, it always comes out as a it always comes out with the decimal point over 1. So I have to multiply it by 10 to get it to be the correct amount. I don't know why. I've never looked it up. I'm sure there's a reason, but I know it's fairly close. We're not physicists here. We're basically digital carpenters just trying to find an angle. Anyway, and then it outputs as output B, which is the BPX here. Same thing down here, except we went a little different. For pixels, because we're starting with the pixels are just declared as the float input, and then we have to calculate the inches, and then we just go ahead and go straight into the APX, so the first two variables get switched on, and then this one has to be divided instead of multiplied because we're already starting with the larger number with the input, which is pixels. But the rest of it's the same calculations going down. But anyway, that is the mathematics and all that, programmed mathematics. We can do the actual mathematics when we draw in a second, but let me see how we're doing on time. We're already past 30 minutes. I spent way too long explaining the code. We don't have time for doing actual math. I'm just going to draw to show you exactly how we can apply this. So using the hex calculator, I want 1 inch. I showed you 0.5 inch, 0.5 inch at a DPI of 300 was roughly 75 and was roughly 150 on the C. That was oh wait, no, I showed you 0. When I said 0.5, I meant from the here to there. That's what I meant by 1.5. What I showed you was actually a 0.25. So because I did 0.25 here, which made 0.15 here across here, which gave me the pixels of, hold on, we're done with the code. We can look here. If we actually look here, you could probably see it. Yeah, it's all there. Let me look at this again and open up the pixel thing again. Yeah, okay. So, as you can see below, and here, C is 75, which we don't put that into any boxes, but A is equal to the X, 38 pixels, and then the 38 pixels was on the X, and therefore B was 62, which was slightly less than that 75, which gave us, okay, so now if I really zoom in here and we tone on grid, we can start seeing what this meant for us here. So this is 38 pixels here. This is 38 pixels. This is 62 pixels. And because we were, running it, if we look at what was it, C again? I'm looking. C was 75 pixels, so this is 75 pixels here. 75 pixel, it would be 75 pixels right here and here. So, yeah. 38 times 2. I don't think that's 75. I think that's off by 1, but we're rounding. This doesn't have to be absolutely perfect. We're just getting the shape. So 38 times 2 is actually 76. It's actually slightly wider than it probably should be, but it also means it's slightly taller than it should be. Weird, I know. Or maybe it ain't slightly taller, but no, it's just slightly wider. Yeah, that's fine. Now, we're going to quickly draw a... Hold on, I'm going to mark this really quick. We're just going to do it here. 0-5 on that. I'm going to add a new layer here. And we are going to start creating a new one. So, with the Hexagon Calculator, make sure I'm showing this correctly. What we want to do with the Hexagon Calculator is we're making a 1-inch grid. And by 1 inch, I mean from here all the way across over to there. So it would be equal to 2C. So we need to take 1 inch, divide by 2C, that's 0.5. Input, my printer's 300, standard 300 DPI. We're doing inches. We calculate. Therefore, A is equal to 0.25. C, 0.5. So yeah, 1 across. B is going to be 0.43 up and down. And let me open up a calculator in front of me. 11 divided by 0.43. Okay, we should be able to fit 25 things going downward. No, that has to be divided by 2. Hold on. divided by 2. Yeah, 12.79 going down. So we're going to have a little over. There's going to be some wiggle room that I'm going to have to calculate later. But let's just get the basic hexagons going. So right here we got A is 75. We need A. And then we need B. So 75 and 129. We'll do that. Let's get to it. A is equal to X here, so 75 width, and then height 129. There we go. Now we could play with, we may want to offset this a little. I'm kind of trying to figure out how we want to offset this a little. I'm thinking if we had a height of 129, we can offset it by half. Give me a second. 129. Oh, 129 divided by 2. 64. We could add a 64 to the y, which the y is already at 32. That means that would be 96 offset, which will give us, a little bit off. And that's going to be important because we can only fit 12, so we're only going to get half on top and bottom. So I'm looking at the, let me try setting this to 0 really quick, see what happens. Okay. I think we'll just leave that at 0. And this is going to be rough, but we're going to try. I'm going to set the line to 10. That's probably still in the way. Give me a second. Move that. And then we focus on dish. Okay. So, now we're going to apply this. Okay. Thinking how exactly we can apply. Okay, we use the line tool, set to black, snap to grid, and from here to there, good, there to here, good, 2 over, down 1, over here, same thing, 2 over. We're going to do this a little fast and dirty. I'll fix it later. And then in the middle here, we go 2 over. And then go up 1, 2 over, down, diagonally 1, diagonally 1. You can round back around. I could take, quite a few minutes trying to figure this out exactly the way I want it, but I'm gonna do this quickly for you guys. And same thing here. Ooh. Yeah. 2 there, 2 here, up 1 and over, down 1 and over. So you can see it's forming. It is forming. The real question here is, what's it going to look like on the other side? So I want to just quickly run across here really quick. Bear with me. I'm trying to record all this in one go. I'm sorry if it comes off as a college lecture. We're getting there. Getting there. Now the thing is, we may lose a half of a hexagon. So we may have to, we may have to adjust our idea of what we are doing here. because we're losing half a hexagon. There are ways we can adjust this and rethink how we want to apply. But it usually involves kind of tinkering and just messing with it. I still haven't. I'm thinking about making a hexagon like an auto builder, but I'm scared of the math that's going to go into that because that gets into arrays, and I am not the best with arrays. I'd have to set up an array, I'd have to have it calculate and check a true or false if it's still on the sheet or not, and it would be difficult for me. You know, I'm looking at this and I am thinking... thinking if it... Watch this, we can just... I'm gonna move this over 1. Now, I already see it locks in. There we go. There. That could be our solution for now. Now, we will lose edges of a hexagon. That is sure. You know, it's like, sure. We can lose a side of a hexagon. That ain't a big deal. I don't like how it's snapping there. I kind of want to do this. Give me a second. Yeah, see, I was cutting off, I think, a little. There we go. Now I can push it back. Snap it in. Okay. So, we got the hexagon. Now, and we're going to lose a small part here. That's fine. Everything's okay. I am thinking maybe a little different. Anyway, from here, you know, once we get one line like this, we can just duplicate and drop down. And then we can apply that to the entire thing. Now, I kind of want to play with this just a little. Yeah, okay, duplicate. I'm gonna bring it up. Give me a second. Yeah. Okay, which one's this one? This one's the one we're going with. Okay, duplicate that one. And then I'm gonna merge those layers together. I'm gonna do this. Duplicate. Ooh. Okay, maybe I messed that one up. We'll focus on, where was it? This one. Duplicate. Duplicate. And then I'm gonna duplicate that one again. Oh yeah, that's getting close. I'm gonna merge these together and duplicate that one. Oh yeah. Uh-oh. I fudged it up. There we go. And then I can duplicate it again. And, okay. Now if we close the grid, there is our perfect 1-inch hexagons. If I can just I can just close all this together, merge it all down. Oh, I copied it all instead. Merge with layer below. And then, you know, it's like, that's kind of like double the size. So yeah, That's how I am creating hexagons. A very complicated, drawn out, confusing process of gibberish. I hope you enjoyed. Oh. Bye. Calculator? I lost the calculator. No. Anyway, bye.